Hi, I'm Shreyash Arya from Max Planck Institute for Informatics, and I'll be presenting our work B-cosification, where instead of training inherently interpretable models from scratch, we propose a technique for transforming existing pre-trained models to become inherently interpretable at a fraction of training costs. So let's get started. Conventional deep neural networks are often highly performant but hard to interpret. For example, an image classifier may successfully classify this image as goldfinch, but it is difficult to understand the reasoning that led to this decision. To understand such models, post hoc attribution explanation methods are commonly used. Such methods provide a heat map highlighting the regions that were important for models' decision and can be directly applied to the existing models. However, it has shown that these models may not be faithful to the model being explained and are often not human interpretable. To address this, inherently interpretable architectures such as B-cos networks have been proposed, which replaces the standard linear layers with B-cos layers. This promotes stronger input weight alignment, leading to human understandable explanations, as shown in the figure, that are also model faithful by design. However, training these models from scratch can be costly, slow, and training data may often not be available, for example, in the context of foundation models. In this work, we bridge this gap to get the best of both worlds. We propose B-cosification, an approach to transform and fine-tune conventional models to be inherently interpretable. The resultant B-cosified models show performance and interpretability on par with B-cos models, while being much faster to train. Let's look at the benefits of the B-cosification in more detail. Firstly, B-cosified models require significantly fewer training steps to reach the same accuracy as their corresponding models. For example, in this figure where the x-axis denotes the number of training epochs, y-axis denotes the accuracy, a B-cosified DenseNet model for ImageNet classification, shown with the blue curve, reaches the accuracy of B-cos DenseNet trained from scratch, shown in orange, in just 19 epochs of training, which constitutes 4.7 times speed up. We find this generalizes across architectures, including VIT models. Secondly, B-cosified models very quickly provide explanations similar to B-cos models. Here we see examples of explanations from B-cos model trained from scratch in the second column, which are human interpretable, compared to the explanations of corresponding conventional model in the third column, which are very noisy. With B-cosification, just one epoch of fine-tuning yields B-cos-like human interpretable explanations, which remain consistent throughout the fine-tuning process. Finally, B-cosification can be applied to foundation models such as CLIP, where training from scratch is costly while using very limited amount of data. Our B-cosified CLIP model provides B-cos-like explanations for the vision encoder in response to free-form text prompts as shown in the figure. Now let's briefly look at the B-cosification process in more detail. We first examine the key architectural differences between the conventional and B-cos models and study which modifications are necessary and how to best apply them. Broadly, we find two categories of differences. Firstly, those preserve functional equivalence. These could be the modifications that keep the model functionally the same, such as transforming 3-channel to 6-channel inputs. This also includes components in conventional models that can be left unchanged without losing the desired properties of BCOS, such as keeping the activation functions between layers. Being functionally equivalent, these updates preserves the model accuracy. The second category includes differences which requires performing a transform that functionally alters the model, such as increasing B to 2 and removing biases, which are necessary to obtain faithful and interpretable explanations. Fine tuning is then required to recover the model's performance. For full details, please refer to the paper. Our method generalizes to a variety of CNN and VRT architectures. Also, despite using very limited data, B-cosified CLIP achieved competitive zero-shot and linear probe performance on many datasets when compared to standard CLIP. Similarly, explanations from B-cosified models perform similar to B-cos explanations across architectures, both quantitatively in terms of localization score and qualitatively. In summary, we propose B-cosification, which provides interpretability benefits of B-cos models at much lower cost. We show that it is better to B-cosify existing models instead of training B-cos models from scratch. Also, B-cosification shows a promise as a means to obtain inherently interpretable variants of foundation models such as CLIP with limited data and compute costs. Thank you again for your attention. The paper and code are available at the following links, and we hope to see you at our poster presentation. Thank you.